Unit 4. So it's a new session series. It is on software integration and the embedded software integration aspects of embedded software testing. We know we need to have a software integration. Basically, there are two things that we need to be understanding. Embedded software integration as such is an activity of the embedded software life cycle, and it should be considered as an activity from both developers as well as testers perspective. That means to say that we are going to have an integration. Definitely integration is an integral part of the embedded software development life cycle. Meanwhile, we are going to test as an integrated unit how it's going to behave. So the second aspect in terms of integration testing we are going to focus. So audience should not get confused with software integration from developers perspective as well as a tester perspective. So it should be separate entity. Developers have their own life cycle aspects in terms of integrating the various modules. Basically here we focus on the testing part of embedded software integration. So that is what we will try to focus and understand. Okay, so to recap on some of the levels of testing, just in order to understand what is embedded software integration, we will see the three levels or three layers of software testing. We know that there are about for example 12 components in an embedded software unit. How they are going to be tested at different levels. We know that at component and unit level we are going to test it individually with the help of stubs or any other drivers or any other methods. That is all a part of the unit testing, where the individual units are under the focus and those units are focused with their objects, data, parameters and all that. And on the higher side, I am coming to the bottom part of the type of levels of testing, system level, where all these 12 units or the 12 components of the embedded software systems is completely put together and tested externally. You can see the arrow mark outside the complete box. You can consider M1 to M12 as a complete unit as a system, and this system is being verified externally with external triggers or events or signal feeds and fault injections likewise. So this is system level. The first one being component level. The one that we are trying to focus in this series of session is on integration, where there are different modular boxes which will be integrated to make it to a system. So we start with this component, we have tested it, the components are fine or the units are okay. Then these units basically grouped into the logical units. So these logical units one, logical unit 2, we have logical unit 3. It can have multiple modules or single module, whatever the way how it can be logically grouped. So logical grouping is again based on the various aspects, as I said in earlier sessions, like its functionality, complexity, and any performance related, then any closed loop control system related. All these feature files, depending on the type of system that we are going to have the various logically divided units into different groups. So that's what we do. So here the example we have 1, 2, 3, 4 units and one M12 as a one individual unit. Here the logically we cannot separate this M12. Let's say it will be separately put. So this is what we do in integration where logical units are getting integrated. So maybe different types of integration testings are there like bottom up, top down, big bang and all. We will study that one by one. And the primary intention is to see that these modules when it is getting integrated how they behave, what is the interactions, what are the inputs and outputs that is getting handled by these logical groups is what is getting tested in the integration software testing. That is the main focus of the embedded software integration testing. Okay, so now we will go in deep into integration testing, the embedded software integration testing. So we will try to understand the definitions, scope, objectives, then we have considerations, strategies. We will take up few examples uh, in this series of sessions of embedded software integration testing. Okay, integration is the process of aggregating components to create larger components. As I said, we have different components. We are going to aggregate them like M1, M2, M3, M4 are individual components. We are going to aggregate as one logical group. So we are going to aggregate those components. So that will become a larger component. We can call it as a component or a group component, whatever it is. So there are 5 groups here in this example, and we are going to integrate that. That's what integration does. So while integrating, there are different types of testing aspects. We are going to create test suite with the help of test environment and get the values for that group and try to get the output. That's what the process of integration is going to take care. Integration testing done to show that even though components are individually satisfactory, the combination is incorrect or inconsistent. So tester's goal is to make sure that it is fine, and tester's goal is also make sure that there are errors, there are issues with certain types of inputs when they are combined each other. So it is not just enough to satisfy individual components like M1, M2, M3, M6. They may work individually fine, but when they integrate each other, what is the behavior of that? So that is what we are going to the tester is going to test it. So the objective is to make sure that the combination of these individual components are satisfactorily working, or if there are issues that has to be brought out, and the inconsistency, incorrectness, all this will be part of the errors or the failures that it could occur while doing the integration testing. Okay, going with definitions that various people in the industry and the web resources that we have, just try to understand. An integration strategy is a decision about how the different modules are integrated into a complete system. The objective of integration testing in the small according to on the B standard 79251 is to find bugs related to interfaces between modules as they are integrated together. That means the objective is to find bugs related to interfaces between modules as they are integrated together. That means we don't have to integrate everything together. We can do progressive integration in terms of first you integrate logical group 1, 2, then 2, 3, 3, 4, 4, 5, etc. Then incrementally add it and see the behavior, how it's going to behave. That's what we do with the modules as and when they are integrated each other. The integration covers both hardware and software. As I said in one of the earlier sessions, there are 2 aspects of integration software testing which we need to understand. So we have hardware involved, software involved. Hardware is involved for what? From embedded software perspective, there are interfaces, right? Interfaces could be using any of the hardware part, like it could be a memory, it could be a communication device, or it could be any signals. All these are hardware parts. So there is a driver, also called device driver, involved. So with the help of these interfaces, they are going to interface with the hardware. So that is what we do with the hardware integration. Software, what we do, we have calculations of the data, algorithms on the complex features. Then we have program flow, that fan in, fan out. I will not go in deep, but you know that software modules, different software modules can be integrated together. It could be app to app, like the data usage, transformation into different low level or high level aspects. Like just to depict what we have is 3-layer architecture. Let us draw in simple nutshell. Okay, the first layer is talking about the app application. Second one is middle layer. You can also call it as a wrapper, or you can also call it as driver level, etc. The third one will be the actual hardware. So we have scope for integration in two aspects. What are those? One is between these two, this and this, this and this. Other one is between this and this. So the one between this and this, as well as this and another application. So we know that applications can be multiple, right? Between application to application, or application to another subsystem app. In case of any subprocess or partitioned apps or RTOS components, likewise you may have. So all this will be called software integration. Whereas the other part where you use the hardware and software involved, such as application to drivers. Here application could be a middle layer or wrappers which will interact with the driver. So this is called hardware software integration. So please remember that two aspects of embedded software integration, software integration, hardware software integration. Both have to be considered and taken care while doing the integration testing. Some industries, what they do is they may not have a segregation of hardware software and software. They might have a purely software. They take care of these small device drivers, interfaces, signals, and all that within the software itself. They don't have that segregation. They can call it as a, in general, integration software or software integration. But most of the industry we have, like aerospace or automotive, we have hardware to software integration and software to software integration. So both are very important. So integration covers both the aspects. That is what this means. Integration covers both hardware and software. The next one, the integration strategy depends on availability of the integration parts. That means if any subsystem library or apps or third-party software as a memory or any signal equipment, etc. So that availability is very important for doing the integration, because we need to integrate them also as part of the complete embedded system. The next one is the size of the system. That means what is the size that system has. how it can be broken up further into different integrated or modular elements. So that is all driven based on the size. Here size means not the lines of code. Please remember, as I said in my earlier class, that size is not the LOC or lines of code. It is the structure and the complexity of the system that is underneath the test of the integration software testing. So that also matters in terms of working out the integration strategy. The next one being the whether it is a new system or an existing system with added changes. So we know that a system is working stable and qualified, and we want to enhance it, or we want to modify it, or we want to add some features. So that information is also important in terms of integration, so that the strategy can be worked out. Then the features or the functionality, that is also important. So what are the various features that needs to be tested? Like features could be externally triggered or internally happening. So all these matters. So basically, a system knowledge is very much important in terms of hardware software integration or software software integration. It's a very key element of the embedded software testing, the integration testing. The last one being the architecture. You know that architecture basically has all the modular and different blocks and cases, use cases and sequences and classes and all that information. So that is also very important in identifying the integration testing strategy. Okay, so we'll move to next. So from the web, I have collected some of the important embedded software integration definitions. System integration, the another aspect of the integration. So we have studied about software hardware integration. Software can also be called as an embedded system. Next one is the embedded software integration, software integration. The third being the system integration, where all the individual complete components like external memory, internal memory, external signals, on-field related inputs in terms of firmware, hardware, software, all this will be put together as a complete black box and tested. That is called system integration. It is also can be called as system testing, but basically they define system integration. That is third level of integration. But before that, software integration and hardware integration is complete. System integration, the task of creating a properly functioning system from its constituent components. So what are those constituent components? One is hardware, other is firmware, other one is software. So all these are constituent components of the system integration. The next one being the system hardware integration. Are the components wired together correctly? That means whether here wired means not the, we are going to check the hardware part as such in terms of any wiring, soldering and all that. That is not the purpose. Once that is fine, we are going to make it validated, make it sure that we are able to interact with those wired components. That is all hardware plugged or pluggability aspects. Whether you are able to interact, read and write through the memory, and read and write to the memory or the external communication with a specified baud rate and specified speed. All these aspects are important. Just wiring may not be sufficient. It has to be done appropriately such that we are able to do the interactions in a intended way what specification or the requirement talks about. So that is what the system hardware integration does. The next definition is system software integration. This typically assumes hardware integration is largely complete. That is, the above part is almost done. The initial step before acceptance testing and deployment. So this is the last step they say. But during the software integration, this is also one of the type we do for putting all together the compiled software piece into the completed hardware. So that is what we do with the system software integration. So we have hardware software and complete system. So these three levels of uh, integration testing we will do it. Okay. The next thing of the integration testing. So basic of the integration, what are the things that we are going to take care of? This primarily what I am trying to put here is integration itself is an activity. This can be taken credit from the tester's perspective as well as developer's perspective. Definitely developers will have to follow some of these uh, strategies or elements of the integration, like he needs to take care of software, hardware and all that. But his focus will be from the developer's point of view, whereas tester's perspective is from the unit perspective in terms of integration and how they are integrated and how we can make it fail, or what are the injection in terms of error or faults that he can try, so that the maximum uh, performance will be done. So integration testing basic steps are as per below. Create a list of all software components. As I said, we live with different components. In earlier example slide, I have put about 12 components. So we need to see what are the software components that we have. The next step is identify the grouping and dependencies between each of them. So once we identify different components, identify the grouping aspects, like how these individual components are coupled each other and what is the dependency of each of them, because one functionality or couple of functionalities cannot be implemented into one piece of software components. Definitely we have to break it down into individual software components. So we need to identify what is the dependency and the intricacies in terms of the grouping between each of them. That is another aspect that we need to identify. Then in the next thing, what we are going to do, list out the strategy to perform these categories of integration. That means we have identified the grouping and the dependencies. How we are going to test this grouping? How we are going to test these dependencies between each software components? That is what the strategy. This strategy will bring out all the aspects of integration, like hardware, software, and system software, or the system integration, to perform these categories of integration. So basically, the list should identify the category of integration, such as, well, I mean, the category of different categories of testing strategy. So what are those? Functionality, performance, subsystem or structural integration. We have a database, we have interfaces, we have control, security or safety, conformity. So these are some of the steps that are to be taken care. Okay. So I will just try to draw a small table here. So what we do with this is basically we will try to identify the list, various integration aspects. First, provide the list of all software components. They want to identify grouping aspects. They want to identify strategy. Then maybe in another column we can have category. So these four things are first identified. In a typical integration test strategy tool or a sheet, I would say this is basically a identifier which identifies these aspects. What are the steps that are involved for integration testing? So first we are going to create a list of software components. So this will list, right? Okay, I'm just trying to draw an example of how we can list out the steps. So first thing is you create a list of component like we did there, M1, M2, M3. We have a M12 right in the earlier slide. So we are going to group together. So maybe we can group M1, M2, M3, M4 as one group. Then M3, M4, M5, M6 like this. So we are going to identify group with that name, like group 1, we have a group 2, likewise we have group N. So how we are going to perform the grouping is basically identifying the similarities of different software functionalities, how they can be grouped, and the dependencies that each group or the software functionalities that it has is one of the identifier. With the help of that, these two columns are drawn. Next, for each of this group, what kind of a strategy I can have, what kind of integration strategy I can have, whether this can be done with the functionality in terms of externally injecting some values, and this can be done with the help of any tools in terms of memory or in terms of speed or communication aspects. This can be tested with a large database and any database modifications or different types of database that we can use. All this strategy will be part of this third column called strategy. And this strategy will have its own type of test environment, type of on the testing aspects. Like strategy 1, strategy 2, strategy 3, 4, etc. We have strategy N. So for each of the strategy, so what kind of a category we can make, like whether it is depending on the hardware, software, any tool. Likewise, we can have a list like what sort of a category. This category has a subsystem dependency, then any database or database automation we need. Then we need any interface or signal specific inputs for this strategy. All this will be listed. So with the help of this, we are going to conduct the integration. So these are some of the main basic steps of the integration testing. Okay, the list should identify the category of integration such as functionality, performance, subsystem or structural integration, database, interfaces, control, security or safety, conformity, etc. Conformity is something like whether the integrated part can be confirmed with the values of whatever the intended inputs. Similarly, security and safety aspects, something like if the requirement says within this limit this has to behave, and upon certain security threat they should lock those kind of requirements can be there. That also needs to be taken care while doing the categories of integration. So each category will have its own sort of inputs, conditions, and expected results. Against that, we need to write the test cases and draw out the integration test procedures and execution. That's what it means. Okay, so we had seen the definition of integration. We have seen the integration basic steps. Software integration will send what is the goal? Basically, to expose faults in the interfaces and in the interaction between integrated components. That means it is not just enough to find out the faults, but also to see the interfaces are properly behaving and interfaces are properly giving in terms of speed, performance, any issues in terms of full load not possible, or it is collapsing after some time, durability, all these aspects will be exposed. That is one of the integration objective. Next one is to find collaboration and interoperability problems and isolate the causes. That means interoperabilities, interoperations we are going to have along with the external systems or subsystems, how it can interoperate with those systems is what we are going to find out while doing the integration testing. Also see the collaboration of different components as we have studied in the earlier slide. The next one is to reveal interface and cooperation problems as well as conflicts between integrated parts. So it's very important to identify the intention of the different integrated parts. Why? Because those parts are basically developed by different people, and if he has a different perspective in terms of requirements understanding, and he would have implemented wrongly, or he would have architected those modules wrongly. So all these conflicts in terms of requirements could come out easily when doing the interface and cooperation testing in terms of software integration. Why I am telling this is because we cannot point out the faults in terms of integration as well, integration alone, but it could be a problem in terms of specification or design also. So all this will be directly or indirectly identified if any flaws are there, the requirements or the specification or the customer inputs. Those conflicts will be brought out while doing the software integration. So these are some of the software integration goals and objectives. Okay, so now testing types. We have seen the levels like hardware software, and system software integration. How we can achieve those, and what are the types that we have, and we can pick up any of this or both of this or all of this depending on the complexity of the embedded software system. But all of these have their own advantages and disadvantages. The first one is the big bang integration. The next one is the bottom up integration, and the last one is the top down integration. So we know that we have different modules and the components. How we can integrate, like what aspects of integration we can take care, whether we can start with a lower level or we start with the higher modules, or we can directly attack the entire bundle. So all this will decide in terms of the integration testing type definition, integration test typing method. So based on that, we can categorize the testing types as big bang integration, bottom up integration, and top down integration. Okay, we will try to study each of them in brief. Big bang integration. This strategy can only be successful if a large part of the system is stable and only a few modules are added. The system is rather small, or if the modules are tightly coupled and it's too difficult to integrate the different modules stepwise. So Big Bang integration, basically this is not used very heavily, I would say, in the industry, but in the industry where we have difficulties in terms of integrating that individual modules, or if it is if the individual modules are tightly coupled or it is too small to test it integration level, what we do is we will go with the Big Bang integration, where we will put together those modules and the small modules which are apart from the main modules together, and we will try to integrate. We will bang it in terms of feeding the values on the field or on the simulation or whatever the test environment that we have. That is why this strategy will be applicable for those kind of systems. So a large part of the system is stable. I mean, we know that the system is working. We don't want to break it, but some features or some modules are added, or some components have been taken out or modified. So what we will do, we will verify that data interface or that aspects which are being added or modified only. So we take with the Big Bang integration strategy for those basically. And the system is too small, as I said, we cannot disintegrate, and it's difficult to test it. The modules are tightly coupled so that we cannot make it apart, and it is too difficult to integrate the different modules stepwise. Like you start with the module 2, 3, 4, then 5, 6, 7 like that. So it may show up on that 2, 3, 4 we can disintegrate, whereas 5, 6 we cannot. We have to test 5, 6 as together when it is integrated at the higher level with 2, 3, 4 or any other modules. Those kind of situation, what we do, we will test it as a whole. That is called Big Bang integration. The next type of software integration and testing is bottom up integration. Here what we do is, okay, so there are few words for Big Bang integration. After all components are unit testing, we may test the entire system with all its components in action. That is what the integration testing does. May be impossible to figure out where faults occur unless faults are accompanied by component specific error messages. That means here with this meaning is we may have to take the credit of components. So what will happen is component testing we have some errors, right? So component testing we have some errors. Issues or faults, or if any pass fail situation is there. So we will also consider that while doing the Big Bang testing, because we are not sure if we face some issues or faults as we have not disintegrated completely. So but still we see some issues or faults are occurring. So what we do, we will focus on the individual components and we will try to attack the complete target in terms of Big Bang integration. So that is what we do with the Big Bang integration. There is a meaning. So the next type of software integration testing is bottom up integration. In this what we do is basically we take up the low level or the lowermost modules, we start with that, and where the minimum dependency is there or least dependency with other components are there, we start with that and we will do it one by one, step by step, and we will do the higher up. Basically this is very useful in most of the systems because errors could be anywhere and it is easier to identify when you start with the lowermost part, so that the higher level models are easier to integrate at a later stage. That is what the usefulness of the bottom up integration. Starts with low level modules with the least number of dependencies using drivers. Drivers, not the hardware device drivers, the drivers for the modules itself. Test drivers it is called, where we have a stubbed caller which calls for that intended low level module, the required parameters for the data, and the expected results are expected with that drivers, and the report will be generated using the drivers. The report could be with the help of printf or whatever it is. But typically the same as the component testing how we do with the instrumentation, but it is done at the functionality at the integration level basically, because the intention is to integrate from the lower level modules till the higher level. That is the idea. The integration can start very early in the development process. Why this statement is put is the development process we will be done with the implementation of few of the lower level layers, and still the complete integration is not done. So without the development team is done with the complete integration of the entire system, it may be difficult for us to do the top down integration aspect. So this can be started as soon as the lower level modules are completed by the development team. So that is a good thing about bottom up integration, and also it will lead to an early detection of interface problems, and these problems can be isolated easily. So before we attack the complete system as an entity, complete entirety, it is better to start with the lower modules, identify the interface issues and the integration issues, so that the higher level issues are less. But the disadvantage is that many drivers have to be used in carrying out this strategy, and it is tedious. You can understand this why, because we are attacking from the bottommost layer of the embedded software system, where we target low level modules, and there are numerous low level modules, and each modules will have their own dependencies, and identifying that, working on the strategy, testing each one of them is definitely a time consuming, and that is the disadvantage of bottom up integration. If there is a scope, money and resources are available, I would suggest to follow this type of integration in a system where it is not very complex, it is somewhat modular complex, and is moderately bigger, not very big, medium sort of embedded systems. This strategy can be used as per uh, the experience. So this is referred basically from embedded software testing book by Bark Brockman and Edwin Wattenboom. We will take an example how integration bottom up testing is done. This is basically from the web source. See, you take, there are two level or two layered architecture design is there, and A is the higher level component, B and C are at lower level. How are you going to integrate with the help of bottom up integration testing? Okay, the first step is test B, C individually. We are going to test it. That means first we are going to verify B, first we are going to verify C. So with the help of drivers, that means drivers means test drivers. For example, driver C will call the C function with parameters and data, whatever it is that is intended for calling the C, and once individually we are done with this, mostly it is done at the unit level or component level. The next step is test A such that it calls B. So we are going to test it A. to make sure that it has to call B, so that we know that the interface between A and B are verified. Similarly, test A such that it calls C, so that the interface between A and C are verified. So if an error occurs, we know that the problem is in A because we already tested B, right, in the first step, or in the interface between A and B. So the error could be at A or error could be at B, and we know that we don't have issue with the B because already we have tested with individually at a lower level, and now we are trying to test A, and we are going to call with the test driver such that A is going to call B and A is going to call C, and if we find out an error or a fault, we are sure that there is no problem with B, but there is a interaction problem. Either A is calling wrongly B, or B is not getting called properly, or there could be error within the A itself. So that's how we bring out the issues in integrating A and B. Similarly, once we are done with A and B, we are going to call A testing such that any interfaces between A and C are tested along with any issues in the A side. So this is how we take care of integration testing from bottom up aspect. So the problem is we are going to test it after B and C are done the A. That's what the negative point about this bottom up testing. Okay. Next we take up the integration testing top down approach. What do we do with the top down approach? It's exactly the opposite way of doing the bottom up. So what we do, we start with the topmost elements, the higher level, and reach the lower level. So it has its own advantage and it has its own disadvantage. So what are those? We'll start with. Control structure is developed in a top-down sequence. So the entire structure of the flow or the sequences that is being used in the embedded software system is being developed first, and those will be used for top-down integration sequence testing. So at every new level, the connected modules at the corresponding level are integrated and tested. That means we start with one level at a higher up, and as we progress, we are going to connect the next level elements or the modules one by one, and we are going to test it. We are going to integrate and test it. Non-existent modules is implemented with stubs. So if there are, as I said in earlier slide, we have seen the complete modules would not have been developed. So but still we have the higher level modules, but those modules, sub level modules, we can stub it and we can test it. Stubbing is also useful when we are not able to provide a different negative values for the higher level values, so that the stub can be modified by the tester for the different types of instrumentation. Advantage is that an early look and feel of the entire system can be achieved. This is what the very important aspect of embedded software testing integration. To understand a system how it behaves based on the knowledge that we have or the complexity that we understand, the best way to test it is just completely put the box under the various conditions, test it from an independent view, how it is going to behave as per the expected system behavior. So then pick up the individual modules, individual functionality, and try to understand where it's going to reach, where it's going to take up the lower level modules. So that we have an understanding of the system, we have a look and feel of the entire system. That's a great advantage of top level, top down integration testing. This is typically important where we have a larger or very complex embedded software system. So, but too huge or too large complex system, they basically they can divide also to conduct both levels of integration testing. They can either do both of them, bottom up as well as top down. Like in that case, what would they do is they segregate the different pieces of the software accordingly. So that is how they take care in a larger complex systems. But both of them have to be done meticulously. Disadvantage is that impact on low level modules may lead to changes in top level modules and number of stubs needed to test every integration step. So here also stubbing is important. Why? Because some of the unimplemented modules or some modules user has to develop with the help of stubs. So those stubs will have to be developed more, and that's a disadvantage. And it may impact the low level modules because low level modules would not have taken care. So that could lead in terms of changes in the top level modules. So that's the disadvantage. So basically we use stubs in top down integration and use the drivers in bottom up testing example, testing integration. Okay. So we'll take up an example, the same example where we have three main modules A, B, C with an example how it is going to be tested, integration tested with the top down approach. Okay. The first step is test A individually. Use stubs as I said for B and C. That means definitely we need stubs because A needs to call in one of the executable that it has, executable line that it has. So we are not doing the B or we don't have a B, so we are going to have a small stub which is similar to actual B and similar to actual C. So first we will test A individually whether with this stub it is fine or not with the help of B and C stubs. Then we are going to test A so that it calls B stub for C. So this is very important because A is going to work along with B and C. And it can call B or it can call C. Each one has to be tested with actual B and the other one is stub. When we are testing C, the B is stub. So that's the third step. Test A such that it calls C. The first time it calls B, second time it calls C. The first time we want to have the same stub for C. The second time we are going to have the same stub for B, so that we know that the working behavior or the actual expected output is same in all this. That is what the approach. So if an error occurs, we know that the problem is in B or in the interface between A and B. So we know that while doing the integration testing, definitely there could be an interface issue, or the issue is definitely with the stubbed part because we have stubbed it and A is getting called and we are getting the error. So if an error occurs, we know that the problem is in B or in the interface between A and B. Similarly, the third step is test A such that it calls C with stubbing B, and if there is an error, we know that the problem is in C or in the interface between A and C in terms of calling mechanism or whatever it could be. So this is how all the errors of A, B, C and A to B, A to C will be brought out. So that is what we do, or we will bring out the top down integration issue. This is exactly the other way of doing here. Here what we do, we start with B and C and we will identify the interface issues either in A or in the interface with the help of B and C. Here we use the drivers. Drivers are at the A level because that is going to drive B and C. So in top down, it is the other way we are going to do with the help of stubs in BNC. Stubs are used to simulate the activity of components that are not currently tested. A disadvantage is that we may require many stubs. That is what is going to happen in top down integration testing. This is an example. Okay, so overall integration testing, top down and bottom up advantages and disadvantages we will list it out. Top down advantage is that test drivers are not needed, or only simple ones are required, because the higher level components that have been tested serve as main part of the environment. The disadvantage is that low level components not yet integrated must be replaced by stubs. This can be costly because there is a definitely effort and cost involved for developing the stubs by the team, and team has to have a knowledge of the uh, B and C for developing the stubs. And the bottom up advantage is that no stubs are needed because we are going to drive it the individual modules. But disadvantage is that high level components must be simulated by test drivers. So in bottom up we need drivers, and top down we need stubs. So it is up to the test strategy team or the test plan team or the test manager or test lead to decide what sort of a strategy is going to work for the particular embedded software testing. It again depends on the various factors, as I said, the complexity, functionality, performance, subsystem, structural integration, databases, what sort of a database it has, whether we have a confidence that it will work, or we need to test for each of the data with the help of all that boundary value analysis, partition equivalence, etc. And control, how the control flow is there for the entire embedded systems, what are the security aspects or the safety aspects. All this need to be considered for deciding the bottom up or the top down integration. We can have both as well, it doesn't matter or doesn't impact in terms of uh, standards or any compliance. Both can be taken care. Okay, so we need to plan accordingly for identifying that. So what is the importance of planning the integration is that by enabling successful integration with critical factors such as objectives, responsibilities, and resource planning. So basically, it will enable. Will have an impact on the outcome of the project or product lifecycle, because without integration, we don't know what is going to behave in the field or with the customer. So definitely, it's very important, and it has an impact on the total outcome of the product or the life cycle. So this is one of the critical part of the product or project life cycle of the embedded software. Time, resources, and personnel are identified for planning that enable successful integration. So as part of the planning of the integration testing based on advantages, disadvantages, types of the integration testing, the time, resources planning, the personal planning, or the tools, all this will be identified. So without having the integration, we cannot identify this. So we need to have planning for the integration and conducting the integrations. That is where the importance of the planning and integration lies. Okay. So integration considerations. What are the aspects that we need to consider for integration? System decomposition, how the system is decomposed. Basically, this is drawn from the design or the architecture. It could be higher level architecture or low level design. Then we need to have a architectural considerations in terms of open or closed. That means the architectural elements can be open or they closed in terms of the downwards layers, and integrated or modular. That means the modularity is required, or the integrated parts as a whole is required. All these considerations we need to take care for doing the integration testing. And the interfaces, how the system is going to interface externally, internally, or with the subsystems or partitions of applications, etc. Then we need to understand hardware considerations. We need to know what sort of a hardware is used, whether it's a real end target or it is a evaluation board. All this will have to be considered. And tools, of course, that tools can be having a hardware dependency or hardware simulation. Likewise, we need to have. This is very much important, particularly in a bigger systems where we have a automated test equipments, ATEs. So hardware consideration is one of the important element of the integration testing. HSIT it is called as hardware software integration testing. Software considerations, where we need to consider the software components such as algorithms. There could be a checksums, or it could be a stringent computations. All these have to be considered. So that is where we do the planning of the integration software testing. Okay, so we will continue in the next class in terms of integration test strategy and the other aspects of the software integration testing.